All right, guys, in this video, we are going to talk about this is technically lesson 3.6. It would correspond with 3.6 from our textbook. However, I'm not pulling this stuff from the textbook because I just honestly didn't want us to have to draw the graphs over and over and over. That's really why. So you're going to see a little printout for this. I'll attach it to the same Canvas page so you guys would be able to print this and be able to follow along. So if you need to print out the notes, then do that. Otherwise, you're going to have a lot of drawing, a lot of graphing that you're going to have to do. So anyways, this whole section is about what's called semi-log plots. And semi-log plots is just a way for us to be able to represent our data with an exponential function or logarithmic function in a way that allows us to put more data points on our graph and also be able to read them a little bit better. And it just makes graphing exponentials and things with very high or very small values much easier. Okay, so there's a couple of really important things here. You're going to end up seeing that the scaling, and specifically in our class, we're only going to worry about scaling the y-axis, but you're going to see that it's scaled kind of weird. So they're not going to be scaled the way you normally would scale a graph, where maybe you do like 2, 4, 6, 8. You're not going to scale it that way. It's going to be scaled as an exponential type thing instead. So you're going to see like something to a power. Most of the time, it would be 10 to a power and do it in that kind of format. So it's a little bit strange. We'll get into it, I promise. But another thing that's important to note is that when you have exponential functions graphed on the semi-log graph grid, it's going to cause them to look linear, which is interesting. But exponential functions, if it's true exponential data, then when it's graphed on log or semi-log graph grids, it will look linear. Okay, now I'm going to zoom in on this a little bit. I know it's really little. So I'm going to zoom in some so you're able to see kind of the data. All right, what we're working with here, this is what we typically think of when we think of an exponential function. So that's what you're seeing on the screen right now. You're seeing our normal situation. So your x's, these are scaled going by like 10, 20, 30, 40, 50, 60. They're only numbering the even, the every 20 or so. So, but that's fine. That's x's. They're going linearly, okay? Is the constant change there. But then look at your y's. It's also changing by the same amount for all of those values that it's scaled. And so that's why we see the exponential function look like what we normally see. It's got that curved kind of behavior. Okay. Now, here's the deal. Sometimes these numbers are really hard to graph. And so if that's the case, that's when we go to a semi-log plot. This is an example of a semi-log plot. You're going to see that your x values are still graphed the same way. They're still spaced evenly, right? But your y's are not. I'm going to show you another example of what semi-log plot graph paper can look like. This is something that we've actually recently used in our class for an activity. And so it might end up looking familiar if you have seen that activity, if we worked that before. So what we've seen before, I'm going to zoom this all the way back out as much as possible because this graph grid is insane. It's taking up an entire piece of paper, okay? But I'm going to zoom in just on the x's down here for just a moment, okay? So down here along my x's, we are looking at it being evenly spaced, 0, 1, 2, 3, 4, 5, right? And they're equal spacings. However, I want you to look at your y's. We have number one, my y value starts at 1 instead of at 0, which is kind of weird, but that's how these work. So they're going to start at 1. And the reason they're starting at 1 is because they're starting where you have 10 to the 0 power, Remember, anything to the 0 power is just 1. So that is starting at 10 to the 0, which is 1. Now I want us to look at this because as you are in this little realm from for 10 to the 0, it goes from 1, 2, 3, 4, 5, 6, 7, 8. But as you notice, the gaps there are getting smaller, right? As you see, the spacing in here is getting to be smaller spacing, which is pretty wild. It's pretty wacky. But that's the way that the semi-log graph paper works, is it has this uneven spacing. And as you go and get closer from 0 to 10, that spacing is getting smaller, right? Then I want you to look at when we hit 10. 10 is the same thing as 10 to the first power. And once we hit that, it's going to, instead of going up to 11 as the next thing, our spacing gets bigger again, and we're going to go from 10 to 20. And now for every single one that we have, you're going to go up 10, right? Until we hit 100. Now 100 is 10 to the second power. I know that's a little hard to read. It's 10 to the second power, right? And once we hit that one, we're going up 100 for each one. So we go up 100, 200, 300, 400, 500, all the way up until we get to 1,000, which is 10 to the third power. So I want you to see here is your Y's are growing at this kind of exponential type of rate. And that causes this to actually look kind of linear. Now, I know that not all of this data looks perfectly linear, and that's because data in the real world application is not perfect, right? So there's a few things in here that are a little bit wobbly, but that's okay. If you get past that point, that data overall looks pretty linear. And so in that situation, we have an exponential model just shown in a linear relationship. All right, so we're going to look here at example 1, and it's using those graphs that showed up at the top. It says, use the features of the semi-log plot above to justify why an exponential model is appropriate for the population of English Americans in the current U.S. from 1620 to 1820. So we're going to look back up here, and they said, why is it appropriate if I see this semi-log plot? Why would it be appropriate to say that this was an exponential model, right? If I didn't have this other thing, if this was my graph grid and this is what was modeled, why is it appropriate for me to say that this was exponential? And the reason for that is literally because most of that data appears linear. If it's on that semi-log plot and it looks linear, that means that it is actually exponential data. So our reason here, we're going to say most of the data appears linear. Okay, I'm going to add as an extra little note on here, just for your own reference. If this happens on semi-log plots, then it is exponential. All right. So that's the first one out of the way. We're going to go to the next question here. We're going to see example 2, and it says that Mr. Passwater tells one of his hilarious math jokes. It begins to spread around the school. The number of people that have heard the joke after 2 minutes is graphed on the semi-log plot above, where the vertical axis has been logarithmically scaled. Which of the following functions could be a model for P? And we have 4 answer options, A, B, C, or D. So I'm looking at this graph grid, and I'm seeing this data. And to me, that data looks real linear, right? But we know that if we are on a semi-log plot, which we are, this is logarithmically scaled on the y, that means that if this looks linear, it's actually exponential. So the first thing I'm going to do is I'm going to eliminate some answer choices because why not, right? Anything that's not exponential, I want to get rid of. So I want you to look at your answer choices, and I know this is pretty zoomed out. It's hard to fit all of this on the screen and it be clear. Okay. But there's only 2 of them on here who are actually exponential. Remember, exponential functions have your variable as an exponent. Well, if you look at A, this is actually linear, which I understand could be tricky because it looks linear. Problem is, it's not. We know this is actually exponential data. This does not count. Okay, that's not exponential. It can't be it. Now, B is exponential. We see that T as the exponent, so we'll come back to him. But look at C. This is logarithmic, which is the inverse of an exponential. We should be looking at exponential, right? D is also exponential. We see T as the exponent up here. So it's between B and D, but at this point, we've made ourselves a 50-50 shot, right? So now the next thing is to figure out which one is it actually. So let's do a little bit of some math, okay? Real important feature, right, is to be able to tell some of the points that are in my data here. So you look at this first point, this initial point. Here, my my x value is 1. Sorry, I'm lying to you. That x value is 0. And my y value, this is the one that's weird. This bottom line is indicating the number 1. So this point is actually 2. 0, 2. Okay, so what I want to do is I want to check what if I calculate that initial value here. What if I plug in a 0? Well, if I plug in a 0, remember anything to the 0 power is simply 1. 2 plus 1 is 3. That is not the output I should have had. If this was correct, my output should have been a 2. Go look at D. We're going to do the exact same thing. P of 0, and this is 2 times 2 to the 0. Well, 2 times 2 to the 0 is 1. 2 times 1 is 2. And that is the one that I wanted. That is my answer. Okay? All right. Next thing. Now, guys, this next question takes up a whole page, right? So we've got a data on a table, okay? And they're asking us to tell which one of these graphs we would like to use to represent this data. Now, they said the table above gives selected values. Which of the following graphs could represent these data in a semi-log plot? Important, it's got to match the data, but not just match the data, it also needs to be a semi-log plot, which means it needs to be logarithmically scaled on that vertical axis, okay, on your y's. So we're going to look here at my answer choices. Look at A. All right, now this guy, it is kind of logarithmically scaled, but it's not on the vertical axis. Look here, it's actually happening on my x. I don't know if y'all can see that very well, but there's a larger space, smaller space, smaller space, smaller space. And so that is getting smaller and smaller and smaller, meaning that that is logarithmically scaled, but it's on the x, on the horizontal axis, not the vertical. That's not an answer choice that I want. Now look at B. This one is logarithmically scaled on the vertical axis, which is great. But look at your data points. My outputs, my y's, should be 40, 60, 90, 135, 203. That is not what we're having. All of these values, all of these outputs are between 0 and 10. Actually, most of them are between 1 and 3, right? So this is not it. I don't have the correct data points. All right, look at C. All right, now you look at C. C's got the correct data. We got 140. We got 260. 390. We've got all the correct data on here, and I see this looks exponential. The problem that we have is we don't have a semi-log graph, right? We don't see that logarithmic scaling. So that's not the one we want, which leaves us with D. Hopefully that's the right answer, right? Otherwise we did something wrong. So here I see that on my X, everything is evenly spaced, but on my Y, that is that logarithmic scale. Now look at your data points. 1, this goes 10, 20, 30, 40. 140, that's good. This next one, 2, 10, 20, 30, 40, 50, 60. That looks right. This data is correct, and it's a semi-log graph, so that's it. All right, next page. Here we've got example 4. We're going to plot the points. All right, so you see these points on here. Plot the following points in the same coordinate plane above. So A, we're going to plot this at 0, 200. So we're going to go 0, and then this is 10, 100. But remember, now it's going to go up 100 every time it goes up. So that is where A would be located. B at 125. Now I need you to be careful because 25, this is a little bit tricky. I'm going to zoom in some more so we get a little closer picture. All right, so that B value at 1, 25. So I should go up to 10, 20, 30, and it should be in here between the 20 and the 30. But I want you to be careful because it actually shouldn't be exactly in the middle between the 20 and the 30, even though 25 sounds like it should be. Okay, now the reason for that is you see this scaling here. This scaling, we see bigger gaps on the bottom. Then these little spacings get smaller and smaller and smaller and smaller the higher the values go until it gets to the next section. So here I'm going to have 20, 30, but my value should be a little bit closer to that higher value of 30. I don't know if you can tell. It's a teeny bit closer, not much, but a little bit, just to make that more specific to being on this type of graph. All right, I want you guys to pause the video, plot these 3, and then come back and check your answers, okay? All right, when you graphed them, your points should have been located. I'm going to just pull up another one so I don't have to regraph them. But this is where your points should have been located, all right? Now, E is the easiest one to mess up, that 4.6, 1.5, because remember that this bottom row is actually 10 to the 0 power, right, which is 1. And so that value, this line on the bottom is already 1, and if I want 1.5, you're going to go up just above that line, a little bit closer to the 2 than the 1, just because of that logarithmic scaling. All right. Last bit, guys. Now, this last question can take a few minutes to get through. I'm going to try to break it down the best that I possibly can because it's weird. It's not that it's vastly complicated, but it is a little bit weird, okay? You remember how we've been saying this whole time, if you have an exponential data on a semi-log graph, it will look linear. Well, in order to represent that linear model, we can make an equation in a linear format, even though the data is actually exponential, which sounds absolutely insane. I'm aware of that. But keep in mind that if we're working with a semi-log plot, and it graphs a line, right? We should be able to model that with an equation. It's just kind of weird, okay? So first things first, remember that the equation for a line is y equals mx plus b, right? So when I talk about y equals mx plus b, and we're looking at this format here, I just want you to correlate these things. Log base n of b, that is my slope. Well, in this sense. And then log base n of a is the y-intercept in that sense, okay? These a and the b, they correlate to your normal exponential function, y equals a times b to the x power, okay? So it all comes together, and we're able to represent exponential data and exponential models with actually using a linear model on a semi-log plot, which is crazy. So like I said, log base n of b is m. Log base n of a is the b from your normal line equation. Now, look at note 2. Our base, you see the log base n, that corresponds with the scaling on the vertical axis. All of these semi-log plots that we're doing are scaled with a base 10 So you're seeing here 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3. But you can scale it differently. So if it was scaled different, you would use a different base on the log. Okay? All right. This is time for us to start our next example. Example 5 says that this semi-log plot corresponds to the data table for example 3. It says write an equation for the linear model of the semi-log plot in the form, and that's the equation that I gave you above. All right. First things first, let's just break down a few things. Number 1, the n value, to talk about the base of my log, the n value is 10. That's what all of these, what the base of the semi-log is, right? So we're going to say log base n is actually log base 10, which happens to be my common log. Okay, so just bear that in mind as we go through this. We're going to be using a log base 10, which is a common log. And that's what we're going to do on most of these things, okay? As long as your base is 10 on your exponential thing, on your logarithmic scaling, then we're going to be using the common log. Okay? All right. Next thing. Let's talk about how we find these values, because I should be looking for slope and then that y-intercept. So slope, don't know if y'all recall from your algebra class, right? Your algebra 1 class, you guys would have learned slope. Slope is the y2 minus y1 over x2 minus x1. Yeah? So if that's my slope, and I need to calculate the slope, maybe, just maybe, it would be great to know some data points. We're going to call the slope, this is, you can call it your average rate of change, right? That is your m. It's also, in this circumstance, we're calling it log base n of b, right? Or in this circumstance, log of b, since my base is 10. But in order to solve and use this, right, log of b, and I'm actually going to, just for the purpose of keeping our notes easier to read, I'm going to say we're going to do log of b equals, and we're going to plug in some points. It's going to be a little bit strange though, so bear with me. Try not to get ahead. All right. So this point right here, I'm going to call this point, let's get our coordinates. The x coordinate here is 1, but I want us to talk about the y coordinate for a moment, okay? Let's try to calculate what that point would have been. I would normally look at this as 10 to the first, so this is 10, 20, 30, 40. But I want you to be aware, be mindful of the fact that this data is not actually linear. Even though it appears so on the semi-log graph, it's not actually linear, which means I can't calculate slope exactly the same way we've done it in the past. It's going to be similar, but not exactly the same. What's going to be a little bit weird is my y values. Rather than actually using the 40 for my y values, we're actually going to use log of 40. Okay, because here we're looking at base 10. So this is log base 10 of 40. Okay. I want us to look over here at this other data point, right? This other data point, same type of thing. I want us to get an x and a y value. So this x value is 2. And the y value we're going to use, we're thinking 40, 50, 60. But instead of just saying 60, I'm going to say log of 60. Because of the fact that this has been logarithmically scaled on that y-axis, okay? So when I use my x1, y1, x2, y2, and all of that stuff, then I'm going to use those values. We're going to use the logs as your y values. This was my first point, so I'm going to say this is x1, and then y1, x2, and a y2. And we're going to plug those numbers in to your slope formula. All right, so we're going to take log of 60 minus log of 40. This is going to go over 2 minus 1. Now, for the sake of, ease and simplification, for right now, we're going to just go ahead and write this as putting it in the calculator, 0.176. It is possible to do these without a calculator, but you have to use your quotient rule and simplify things down and just get expressions. For the sake of simplification right now, we're just going to leave it like this. But in the future, we may do more. Okay, so just be mindful. That is log of b is about 0.176. And that happens to be like the slope value. All right, let's recap. What do we have? Y equals my slope value we just got, the log of b, 0.176x. And then we're going to say plus, we still don't know, log of a, which is what I need to find next. Okay, so here's what we're going to do. We're going to plug in a value, a point, if you will. We're going to plug in, let's say, just do the x1, y1. If we plug in that point, y'all, this is what we get. The y value we're using here would be log of 40. Then we have 0.176 times the x value plus log of a. Well, in order to solve this, we're going to need to subtract. This is 0.176 times 1, so it's just 0.176. I'm going to subtract that on both sides. And guys, if we type that in the calculator, log of 40 minus 0.176, you will get approximately 1.426 to be log of a. All right, important values, guys. We got log of b, we got log of a, important values. And now I can use them to write equation. They asked us to write an equation in that format. They even wrote this out. So we're going to say y equals, and then the log base n of b. Remember, we had the log base 10, right? Common log of b. That was 0.176. And put next. Plus log base n of a. Remember, log of a, we got to be 1.426. That is my equation. Now that we've done that part, on to the slightly more challenging part, that is the easier part. Now that we've done the challenging part, they're asking us to now write an equation in exponential form, y equals a times b to the x power. So we're going to write in that format. Now I want us to go back and use some of our values. Here this says log of b, which equals 0.176. I'll write that out. Log of b, 0.176. Right? Another relationship we knew was log of a. Remember, I'm trying to find a and I'm trying to find b. So why don't we use the values to help me find them? Just remember that when you have these logs and there's no base written, it is automatically 10. So if you want to write that in there, you can. It does not hurt. Okay. So now we're going to change these and be able to solve for a and b. Look here at b. Okay. I am going to change this one to be exponential form. That will get b out of the logarithm. So the base of the log is 10. We're going to write this as 10 to the 0.176 power. That is equal to b. Then if you type this part in the calculator, it will tell you that b is about 1.5. Okay? The next thing I need to do is calculate the a value. So my a value here, we're going to do 10 to the 1.426 equals a. So just convert that to exponential form, raise this to that power, and it's going to give you 26.669 for a. Once you know these values, plug them into this formula. Y equals a, which was 26.669, And then we're going to say times b, which was 1.5, to the x. This is the exponential equation to represent that data. All right. Ooh, I fell. So I'm going to zoom out here just so you can kind of see what we did on that problem. I know that one's a doozy. Most of this stuff seems like fun and games till we get to that question, then it gets pretty crazy. All right, y'all. That is it for the semi-log graphs. I will see you in the next lesson. Good luck.